All right, let's dive right into this explainer by looking at a total biological mystery. And the crazy thing, it's happening right now at this exact second, in literally every single living organism on Earth. Welcome to Mastering Osmosis. We're going to map out exactly how this invisible molecular process works.
It sounds super simple, right? But honestly, the answer is incredibly profound. Did you know that the constant, everyday process of water moving in and out of your cells is quite literally what's keeping you alive? This vital mechanism doesn't just keep your body running. Mastering its rules is an absolute must for securing those valuable marks in your O-level biology exams and for understanding real-world macro-level stuff, like plant turgidity or even how certain medical treatments work.
So here's our game plan for today. 1. What is osmosis? 2. Understanding water potential. 3. Animal versus plant cells. 4. Common osmosis mistakes. And 5. Final exam review. Let's get into it.
Section 1. What is osmosis? Okay, here's your gold standard, commit this to memory definition. Osmosis is the net movement of water molecules from a region of higher water potential to a region of lower water potential across a partially permeable membrane. Think of it like two rooms separated by a mesh screen door. The room packed with more people naturally pushes into the room with fewer people. Look at those dynamic arrows moving left to right. We can literally track this net movement of water molecules driven from the crowded, high-potential side right on through to the less crowded side. Now, what's really fascinating here is that labeled boundary right in the center, the partially permeable membrane. It acts exactly like our mesh screen door. It's highly selective. It lets specific, tiny molecules like water easily pass through while completely blocking out larger solutes. The whole flow from high to low completely depends on this specific structural boundary being there.
Section 2. Understanding water potential. Look at that big 0. We anchor the entire concept of pure water potential at exactly 0. Why? Because pure, unadulterated water represents the absolute highest amount of free energy available for water molecules to move. Its potential to do work, to physically move, is maxed out right there at exactly 0 on our scale. But watch what happens to our energy gauge when we toss in some other elements. As solutes like salt or sugar are added, they actually bind to the water molecules. This effectively drags the water's potential down into negative values, heavily reducing its free energy. So the physical flow of water is always driven down this gradient. It's basically sliding from that pure, zero-energy state toward an increasingly negative energy state.
Section 3. Animal versus plant cells.
Let's put these two cell types side by side in our macro-level cheat sheet. An animal cell completely lacks a rigid outer wall. So, in a dilute solution, meaning high water potential outside, it bursts. That's a process called hemolysis. But in a concentrated, negative potential solution, it shrivels up, which is called crenation. Now check out the plant cell below it. Its rigid outer boundaries actually protect it from bursting, making it nice and firm, or turgid instead.
Let's zoom way in and magnify that animal cell scenario. When a red blood cell is placed in a dilute solution, the external water potential is closer to 0. Look at those thick directional vectors rushing in. Water rapidly flows down the gradient and floods into the cell. Without a rigid cell wall to protect it, the membrane simply can't handle the pressure. It expands, fails, and we get hemolysis. The cell literally bursts. Now, let's flip the script. Look at this transparent cutaway of a plant cell sitting in a concentrated, highly negative solution. Water is actively being pulled out of the cell. Do you see the structural difference here? The thick macro outer cell wall stays perfectly intact and rigid. But if we peer inside, the inner micromembrane actively pulls and peels away from that wall as the cell loses volume. This visual right here, that's plasmolysis.
All right, let's trace this step by step in a chronological flowchart. When a plant cell is placed in pure distilled water. Step 1. The external water potential is higher. It's right at 0. Step 2. Look at those highlighted water vectors forcefully entering the cell, moving down the gradient. Step 3. Instead of bursting, that strong structural cell wall pushes back against the internal pressure. This physical resistance is what creates structural turgidity. It is literally the exact reason your houseplants stand up straight after you water them.
Section 4. Common osmosis mistakes. Okay, here is the absolute most common trap that trips up even the most focused learners. You've got to know the difference between general diffusion and osmosis. General diffusion is just the movement of any particle down a concentration gradient, no membrane required. Osmosis, though, it is strictly 100% exclusive to water molecules, and it absolutely requires that specific partially permeable membrane we highlighted earlier. If you aren't mentioning the membrane in the water, you are not talking about osmosis.
Here's another huge misconception, thinking that this biological transport requires active cellular energy, like ATP. But look at that label. No cellular energy is required. As our 0 to negative energy gauge showed us earlier, osmosis is purely a passive process. It's totally driven by natural physical gradients. Think of it just like a ball naturally rolling down a hill.
Finally, Section 5, Final Exam Review. Let's lock this in with a rapid-fire recap to secure those marks. Rule 1. Water always moves from a region of high to low water potential. 2. It strictly requires a partially permeable membrane. 3. Water potential is just a measure of the free energy of those water molecules, maxing out at 0. And 4. Structurally speaking, animal cells risk bursting, hemolysis, while plant cells use their rigid outer walls to become turgid.
I want to leave you with this direct quote straight from our source material. Practice drawing diagrams that show osmotic changes in cells, as visual aids can help secure those extra marks. Take that vital advice to heart, guys. Explicitly visualizing these component variables, drawing out the boundary walls, and sketching those dynamic directional flow arrows, just like we mapped out today, will absolutely save your grade. Seriously, if you can draw it, you truly understand it.
So, I've got to ask, how will you draw the osmotic force vectors for your next exam scenario? The next time you face a biological mystery, remember to pull out your mental whiteboard, properly label your membranes, and trace the flow of water potential. Thanks so much for joining this explainer. Stay curious and keep exploring.